Hello, we'll talk about First Law of Thermodynamics today. This is a law which is an expanded view of the energy conservation principle. So to recall, energy conservation is based on accounting for energy of a system and how a system may interact with the external world, and its energy may change as a result of the interaction. So in a broad view, you can say you have a system can be anything. Maybe so there's a human being here, that's our system. So let's see, there's a human being, that's our system. And we want to study how this person's energy may remain same or different, change with time. So human being is a very complicated system in the sense that we breathe and we do work on other system. Other things can push us, give us kinetic energy. So if it's outside world, it's interacting. So this is my system, and then this is outside world. So we can say they can exchange energy. So at some point, we don't know exactly how much energy it has. It's a pretty complex system. We might say at time t1, this human being has energy E1, and if I look at this energy, still looking abstractly, is its energy at some other time. Maybe it's got with the outside, it lost some energy, maybe it gained some energy, and in the end over here the human system has a different amount of energy. So this is a time t2, and it's got energy E2. Well, outside world, I can also look at the energy of the rest of the world. You can say its energy outside is at this time is the outside world, not out. Let's call it surrounding, or surrounding, and it's still interacting, but at this time the energy outside is E2 surrounding. Now if I say, this is the only two things in the universe, which is not the case, but say we have isolated so that this human being and the rest of the universe is what the surrounding is, then you will say these together, that's all there is. So this together, you can say, is another system, which is you can say isolated system. There's nothing outside of it. So what we will say is energy E1 at time t1, it has energy E1, this isolated system, plus E surrounding 1. That will be the energy here. And energy over here of the entire isolated thing is going to be at T2 will be E2 plus E2 surrounding. By energy conservation, we mean that energy of this isolated thing here is the same as energy over there. So by conservation we mean just if I able to account for every source of energy that happened. So we say E1 plus E1 surrounding is equal to E2 plus E2 surrounding. So you can say I may not know these values, I may not know exact values, but we can say that the difference in the energy of the person, so it's E2 minus E1 is the change in energy of the person, system. If I bring this on the other side, is equal to whatever the energy was lost by the surrounding, and vice versa. Energy 2 surrounding minus energy 1 surrounding. So if this was a plus, then the other thing lost same amount. So this statement is the statement of energy conservation, right? So this is the same statement as that. So this is energy conservation statement. Now we would of course this is very complicated and abstract. We would really don't want to have to deal with this. We just want to deal with the system. And so can we say something about this? And that's the kind of focus of the first law of thermodynamics, just to be able to say as it's interacting and how this energy could be changing. What would change? What kind of mechanism by which the change in energy can take place? All right. So I'm going to erase this and try to get the first law of thermodynamics in the next board. Okay, so I'm going to look at, I have a system, and it has some energy E1 at time T1, and at some other time I look at the system, it has E2 at time T2. And so it has interacted with the outside world. So there is, this system can interact with the outside world. So it's interacting with the outside world. So we'll just draw like that. That means energy can flow. So we want to know how the energy flows. So if we look at it, what we have done before is that let's look at a block. So here's a block of instead of person, let's look at inanimate object, and very simple one. So say this is a copper block. This is my system of copper block, and this can this outside. All right. So how can the energy of this copper block, what are ways it can change, right? So if you look at it from the perspective of what we have done before, so this is the Earth, and there was a center of mass of the copper block right in the middle, and if this was T1, and at T2 center of mass is over here. So we said if this was H1 and this is H2, then you can say that there is a change in potential energy. Remember that? So one way, so let me kind of account for it as we look at this very simple system. So you can say, well, over here, change in energy of this copper block. So that's my system. One way I can change energy is just lift it up. or lower the height, right, from the ground. So this would be change in energy, potential energy of the center of mass. Is based on the center of mass. Another way its energy can change is maybe this copper block, the center of mass has some speed v1, and maybe this is going at speed v2. So it's moved, or it might even just go v1 this way and go up. It's been going up, so it's kind of v2. Right? So some speed here was different than that. Then we'll say, you know what? This kinetic energy can change. So that's the kinetic energy of this also center of mass. Another way we have learned to look at energy is this can rotate with some omega 1 about this axis, say, and maybe this is rotating at different omega. Then we say, you know what, the whole block is rotating about cm. So this is delta kinetic energy about axis. So this is the whole body is rotating. This all had to do with the system as a whole being displaced or moved. So this is what we have done before. Now copper block consists of a large number of atoms and molecules. When we do this, we're really not looking at the energies of the motions of the molecules, etc. So there is also kinetic energy as well as potential energy, because electrons and protons and electrons, they're interacting inside the copper block. And that's missing from this picture, right? But they're also nearly impossible for us to find out in detail. So we'll just take an on average behavior of that motion and kinetic energy and potential energy. So we just look at the entire picture and just call that internal energy. So we can say change in internal energy. And usually letter U is used for internal energy. So this is called internal energy. You have learned that these can be changed by some external force moving the whole object, right? So this is from work energy theorem we have studied. And the question is, how do they change internal energy? So let's call this part delta E external, and we can call this delta E internal, just for our accounting purposes. All right. So to change this, the way we interact is I take the copper block and apply external force on it, which is not the gravity, right? Gravity is already taken into account by this stuff. Other potential energies are also accounted by this stuff, right? If this was a spring attached to a spring. So we learned this. You need external force and external torque to change this guy, external force change. So this one so external force and external torque that do not change the shape of this, do not compress it or change the shape of it. So this to change this, we require external force or external torque, right? We require external force, external torque that do not affect the shape of this thing. That does not change shape, because shape part, say if I take this block and compressed it and make it a little smaller, that will have the effect of changing the stress inside, and that will store an internal energy. All right, so let me erase this and I'm going to come to a clean board. Okay, I'm back. So we're looking at a copper block as my system, and when we would say how can I change the energy of this? What the change energy look like? Okay, so we had a system where system can be moved as a whole. I can move the copper block as a whole, and that we identified those kinds of energies as external. All right, and then if I were to compress the copper block and I changed internal bonding and cause the strain inside the copper block, there will be stress inside, and there will be a deformation energy that will be stored in the copper block. That we're going to use, those kinds of energy will be internal to the copper block itself. All right. We want to look at those kinds of energies. All right. And first law of thermodynamics. First law of thermodynamics actually is stated for that part. Although it is understood that if this part was not zero, you have to deal with this. All right. So this is the fundamental energy, and we're gonna look at how to change that. Internal energy. So I already talked about one mechanism of say compress the copper block. I have a copper block, and what I do is I apply a force on it. So I apply a force from all directions. So I cause a stress inside the material, and maybe the volume decreased by that much. So it used to be volume V. V1 goes into V2. So this at time T1 is like this, and time T2 is like that. And this is volume. So you know delta V is V2 minus V1. Delta V over V is the strain. So this is the epsilon. And stress inside the material will cause stress inside the material, which will be bulk modulus. So stress will be bulk modulus times this, because I'm changing the volume, right? If I'm changing the length, it will be Young's modulus. But this whole thing I'm changing. So if you look at energy, we saw that there's a concept of energy per unit volume, and it was a half bulk modulus strain square. This is unit of pressure, right? This thing had a unit of pressure. Pressure was Newton over meter square. So if I just multiply by Newton times meter cube, so this is energy joules per meter cube. So this is joules per meter cube. This has no units, and this one has unit of pressure, right? So this is energy density. If I multiply by the volume, say V1 or V, so this is assuming I've made very tiny amount of change, okay? And count that whole thing as a volume. So this will be amount of energy that's going to be stored inside the bonds in intramolecular forces, inter and intramolecular forces inside the material. And that's like, there's no way to independently look at all those molecules. So I'm gonna have to look at as a bulk property, just whole property. So this is one way you can actually change this internal energy. So this type of thing is called work. This mechanism of changing internal energy is because there's a force involved here, right? And you remember force times distance is work. So this mechanism is called work. Mechanism of changing. So this mechanism changing energy referred by work. So so we'll say if I wanted to take an account of it, if I do a positive work on it, like this outside agents, so this is outside from outside, right? The outside agents have done the work on it, so the energy was lost by the outside and energy of this thing is gained. If I say, hey, I want to count it as a work by the block, which is kind of a little ridiculous right now, but I can use a notation like that, and that means these arrows will be flipped backward, because for every force there's the opposite force by the other thing. So this is, I'm applying, suppose you are applying this force, then the block will be applying opposite force on you. So if I want to write in terms of force by the block, I'll just get a negative value for this, right? So sometimes we say there are two notations for writing this: work by the block, a work by the system, a work on the system. So we can say work on system, or we can account as work by system. That's one mechanism. And I'm going to erase this. There's another mechanism that's also possible that changes that. Okay? Okay, so we just introduced one mechanism for changing internal energy, and that has to do with changing the shape or the volume. So this has to do with if volume or shape changes. So we're looking at the block. So here was the system. We're looking at system, which is just a copper block for simplicity. And we talked about whether this work can be work on the system or by the system. So when I compress copper block, I'm putting energy inside this, and that will be it can be a positive number or negative number. So if I'm saying that this should be go up if I compress, and if I use work by the block, that's the physics way of thinking. So work by the system, all right. So work by the system will be kind of negative of what we're looking at, the formula, right? So it should be so we will say work and work minus work by system. So that will be, so we will write down that would be equal to one of these. So we'll say delta U internal, how much energy can change? Well, it will be how much work I did on the system, but I should be, if I'm going to write it by the system, then I put a minus sign here, by system. And if that was the only mechanism, and I'll be done. And actually that will be the only mechanism if I have a thermally insulated. So if you had a copper block and you put a insulating material so that no heat can flow, right? So there's no it cannot flow, but I had, in terms of flow of energy, I still had something I can press on this. So I could press on this and compress it. but I wasn't allowing any other exchange of energy. There's the only way to exchange. So that will be it. However, that's not always the system I'm interested in. I'm also interested in maybe heating the copper block or cooling the copper block. So how can that be? So the copper block is this, and so say it's a temperature T1, and if this is my system, if I want to put this copper block in an oven, so let's call it over here, outside system is oven, and oven it at temperature T2, which is greater than T1. If that's the case, then energy will flow in from outside, and this energy is rather difficult to actually measure, but we know one of the natural facts of life is if you have a temperature difference, then energy tends to flow in. It's and maybe changes the inside the molecules that go faster. A copper block starts to vibrate more. So it goes into all the vibrations and kinetic energy and also potential energy of the molecules inside the atoms of the copper block. So those things I have, but I can't really take that. There's no way to measure them. So just overall, we'll say how much energy oven is using in order to change the temperature of the block. So the T1 will eventually become T2 because I'm going to keep supplying energy from the oven is also getting supplied energy. Suppose you have electric oven, you're getting electrical energy inside the oven to make it all the way to the copper block. Okay, and that mechanism is not changing the shape. Excuse me, not changing the shape of the copper block, right? So it's not of the work type. So I need to be able to account for that, and that is called by the mechanism of heat. So the second mechanism is by heat transfer due to temperature being here different than temperature there. If the temperature was same, if you put copper block say at room temperature and the oven is at room temperature, there is no energy change between copper and block and the oven. So the energy changes, energy difference, energy changes of the block or energy into the block or out of the block only happens if the temperature is different, right? But if in this mechanism, heat transfer, there's no heat energy by itself. Like oven does not have necessarily an energy called heat energy. It's got what we call, when you turn the oven on and it say your electrical oven and the filament glows, what does it do? Filament is not there's no heat such thing called, but that glow that you're seeing, and there are lots of energy that you see unseen, they're basically electromagnetic waves. Maybe you didn't know that. So that energy that you're seeing is that they are electromagnetic waves of a frequency that your eyes cannot see. They are in infrared. So glow red part you see, that's pretty much the edge of what you can see. And beyond that, things of a little higher wavelength and lower frequency have considerable energy in them, and they are the ones which actually make it all the way to copper block. And in a way, oven is a source of a special type of light, right? And the light shines on copper and is absorbed by the copper electrons and and that's what heats up copper. So there's no like a thing had a heat energy. Thing produced photons, things produce electromagnetic waves. And so that's what we say energy transferred rather than heat transfer than heat. All right. So heat transfer. We don't say heat energy transfer. So never say it that way, because that's just a very misleading. It says the oven had heat in it, heat energy in it. It had heat, but not heat energy in it. So sometimes people write heat energy here, and that's totally not acceptable in the physics community. Maybe it's acceptable in some other community, but physics people really frown upon using the word energy to go with heat, because they have been wrong. Actually, they used to be called, and almost 200 years ago, it was proven that that's not the case. Okay, there is no such thing as heat energy. There is such thing called heat, and that just means energy in flux. I'm going to call energy in flux by a new name called heat. But the system A, which is giving energy to system B, system A does not have heat in it. Okay, it just the energy flow that's occurring by this mechanism of difference in temperature, and this mechanism of electromagnetic radiation. Basically, we are doing radiation to heat other object. This radiation energy transfer from body A to body B via radiation, we call it heat. The mechanism is called heat, but there's no named heat energy. There is a more in, you can go check this website. For more further discussion on this point. All right, so we'll say now we need to know a convention just like this one. For the heat, the mechanism is the direction. If this is positive, energy goes into the system. So we, instead of work by system with, so we say into the system. Okay, so that's another caveat you have to remember. So we'll just use although we use delta for the energy change, but this one is already the transfer of energy, right? So we just use letter Q, not delta Q. Some books use delta Q also, but more traditionally we use Q, and Q into the system. So it's positive when things go into the system. You can see that this by minus sign is going to be positive if energy of the system goes up, right? If I work on the system, then this is positive. This heat into the system is positive. So it makes consistency, right? It's a very consistent way to talk about. And make sure you understand the science here, because you don't want to say, okay, while the copper block's energy went up, and you're subtracting the energy just going into the system because you're wrong convention. So this is the statement of first law of thermodynamics. So we'll have some example to numerical example to illustrate this idea. Okay, but this is just one part is addressing. I want to make sure to recap that this is once written this way, it's only addressing what's happened to the internal energy, and this was to change the block's center of mass height, center of mass motion, maybe rotation about the whole block, right? Now I use the word block. This is true for all systems, and I started initially with looking at the energy of a person, and we'll come back to it as in our example, okay? But when you're looking at this, you have to be cognizant of the fact that often thermodynamics is written for the internal energy. But when you're using it, you have to make sure that these other things are also accounted for. Because energy conservation happens for the full energy, not just for internal energy, but the full energy. I'm going to stop here. I'm going to think about some examples, numerical examples to share that with you. I'll see you in another video. Okay. Hello. We are going to talk about numerical examples in application of First Law of Thermodynamics. Calorimetry is one very important example where what we do is we don't let the volume change that much. So there is no work involved in the process, or very little work is involved in the process and for changing the energy of the system. So the only mechanism left is the heat mechanism for changing energy. Okay, so let's see if you can help me out with this. So an example will be, say I have a system. It has a beaker with, let's see if it's got 10 kilogram H2O in it. Kind of weird way to say. I'm going to use kilogram H2O rather than milliliters or liters, things like that. It's got 10 kilogram H2O. And this is at, say, 25 degrees Celsius. So this is my system, system A. So let's call this system A. And over here I have system B, which has 5 kilogram H2O, and this is at, say, 85 degrees Celsius. It's pretty hot. And then I come in here, make a hole and drop it in there. So this is B and this is A. And this, you can think of this as isolated from the rest of the world. So you can see that energy of A plus energy of B has to be fixed, right? So you have energy of A. I don't know how much A has energy. It's got some. So we'll say change in A plus change in B equal to 0. That is energy conservation principle for this isolated system. By using that and knowing that it takes, this is the data, it takes this many joules to change temperature by 1 degree Celsius, I would be able to figure out what's the final temperature. I'm going to apply this to this system. Okay, so first thing to notice is this energy here, I'm not changing, so they're all internal. So right now I can just say, hey, this, everything is just internal. Internal A, delta U, internal D. Each one of them will, according to First Law of Thermodynamics, will have a work way to get in here from B into A, but there's no work done. and there will be a heat wave of A. So each one of them is work by A plus Q into A. So that's this part. So that's the first part. There's a second part. Second part will look similarly. Work by B plus Q into B. So this is actually minus. These are minus. So that's the first law. So the left hand side here is that. Okay, we are assuming that, you know, A, the volume of A by itself didn't expand. Of course, when the water came in, A plus B is A plus B volume. But the volume of A itself did not change, right? So we will just assume that. So this is equal to 0. This is equal to 0. So Q into A plus Q into B. Well, it turns out that Q into A will be whatever the final temperature, both will come to the same temperature, right? So Q into A is not the exact middle of these 2 points, okay? So if the exact middle will be 25 plus 85 over 2, right? So this will be exact middle, and that's going to be 0. So you would think 55 degrees Celsius, this will be wrong. If you just say, well, yeah, I got 25, got 85, just in the middle. No, but you will see why it's not going to be in the middle. Q into A will be how much, so I don't know the T final, let's call it T final, but I know it started 25 degrees Celsius. So that's the change in temperature times the amount I had was 10 kilogram. So if I multiply by this quantity, 4,184, that's how much is Q into A. I want to make sure that this is going to be positive number. You can see that this is going to be bigger than that. So this is going to be positive. Just makes sense in terms of, you know, conceptual thing, right? This one should be negative, the same amount, but I can account for it directly from B. So from B, it's going to look like 4,184 joules per degree Celsius. That's like that. That's the unit, joules per kilogram per degree Celsius. Times, I got 5 kilogram times, well, I have a final temperature TF minus TF minus 85, and this should equal to 0. So this is an equation in TF which we can solve for TF, and you can see that there is energy changes final minus initial. This energy is final minus, and this gives positive and this gives negative, just correctly, right? I'm going to erase this and I'm going to try to solve this for TF. Okay, how do I solve this for TF? It's really simple. You can see that here this number cancels out, so I didn't really need to know. And then the rest I can expand. This 5 will cancel this, give me 2 here. So I got 2 times TF minus 50 from the first. From the second, I get TF minus 85 equal to 0. So I have a 3 times TF equals to 5 here and 135. So the TF is 135 over 3, which is not 25 plus 85 over 2, not that. That would have given me 55 degrees Celsius, right? So this is not. I got something like that. I'll do more examples, okay? Okay, we're gonna have an example of a steam power plant, and we're gonna apply first law of thermodynamics numerically to this, okay? So we should say first law to a steam power plant. Okay, so what's going on here? We have something, a closed environment in which water gets heated, becomes steam at very high temperature, and that steam is then turns the turbine fans on, and that rotates some electromagnetism effect there, and it makes electricity, and that goes to the homes and so. So energy comes out of the steam that actually makes it a just kind of moist steam. This is like a dry steam. This is moist, or just a mist kind of thing, a lot of droplets, and then you pass some cold water around the pipes while the mist is going through, and it condenses into liquid water at say room temperature, and then this liquid water, then you pump it in back to the system. So it's kind of a closed system and goes in a cycle. So what's the system here, which is of interest? The system is this water. So, and I see at 1, this is where the heat comes in, right? This is the heat mechanism. So energy, this is the rest of the world. Okay, let's rest of the world. So at 1, the heat comes in. At 2, heat actually leaves. At 3, some energy leaves, but it's not the type of heat. I can't call this because of the difference in temperature. This energy is coming out. It's a mechanical, right? It's hitting the fan and rotating the fans. It's not compression, expansion, but it is a mechanical energy, and that's what we are calling generically calling work. One form of work was when this was compressed. So when I do that, so at number 3, there's a work, but this is work is leaving energy, leaving the water. That means minus work on turbine. This is by water. That's why it's by water. That's why it's negative. This itself is negative, so the negative becomes positive. So it's actually leaving. How about this guy? At 4, I'm pumping the water, so some of the energy that I made here, I need to spend to get the water back into the tank. So at 4, is actually work. The energy is increasing. So this energy is negative, and this energy is positive. So minus work by pump. I'll make sure. So, but it's back to the water some state here. So if you had a T1 and the water went all the way back at T2, so let me ask you, what's the energy change of the water? Think about it. What's the energy change of the water? What do you think? In the full cycle. just go all the way around, come back. So I took, say, some water molecules, this much. I followed this guy, went all the way here, back to the same place or same state. So that, if you said the overall change in energy is 0, you will be right. So delta E of H2O, one cycle, that phrase is cycle, I went in a cycle, back to same place. That's equal to 0. So the way here I can say is this comes in, so this is all internal. So delta U H2O internal, one cycle. And so now I can write that as thermodynamics. So all the Q's, Q into H2O minus W out of H2O equal to 0. So that's the overall first law. But let's look at the accounting. We so the Q into came in here. Let's look at some numbers. So Q in, suppose you had a 5,000 joules, and Q out was maybe 2,000 joules, and the amount of work you had to pump was 200 joules at this time. So the question would be, how much electricity this power plant was generating? Well, we can answer that question by just this. Q into, this is a plus, but this one is minus, because the way this is supposed to be positive for in. So this will be 5,000. But this arrow is going out, so I would have to minus 2,000 joules. So that's the net in. So this is the net in. So that's the Q. Okay. That net heat exchange with the environment. The work supposed to be out. So this is the work out. Work by the system on the outside world. So I have a work, we're talking about work in 3. And so this will be opposite of that, right? So 200 joules. So this much energy increased because I actually did some work onto the system. So that's equal to 0. So amount of work that must have been done, I can solve this. So this will give me 3,000 plus 200, 3,200 joules. So that's how much electricity I got in one cycle. Now, if the cycle took, say, 10 seconds to complete, so where the whole cycle took 10 seconds to complete, then the power of the plant will be, say, 10 seconds per cycle. Then the power of the plant will be how much work, how much electricity the plant generated over the time it took. So you have 3,200 joules it generated. It took 10 seconds. So this is 320 watts. Not very powerful plant, right? It's not working like megawatts, things like that. So you'll have a system like this many times more in an industrial setting. So I'm going to stop here. This should complete our discussion on the first law of thermodynamics. Next we're going to talk about is efficiency of the power plants and heat engines, and that should complete our course for this semester. All right.